I'll discuss a bit about galaxies at redshift greater than 6. Reasons have been discussed in this conference, so I will just go through this. First off, I will present various observational results which are coming from JWST, focusing on my own view why certain observations are important when we are trying to model galaxies. It will be incomplete. You will hear more details on these observations from Yogesh tomorrow. So basic idea of galaxy formation, we know that if you look at the dark matter, basically you assemble a dark matter halo starting from smaller clumps at different redshifts. This is what hierarchical galaxy formation model will do. But what we are interested in is that let it happen in a system which is self-consistent. Then you look at what happens in individual dark matter halos. And typically what happens is that the dark matter is useful for everybody here, for some of us it is useless because you don't see it. Okay? So we are worried about what we can see and what we can analyze easily. So it is related to gas. So when you think of gas, how do you convert this gas into stars and how you evolve them on galaxies? There are various processes involved. One is cooling and collapse. That leads, some fraction of this process leads to star formation. Star formation means you are thinking of a nuclear reactor running for some time and exploding in various forms and transmitting whatever cooked material into the surrounding region. So this can happen in various forms, mass loss due to planetary nebulae stages, stellar winds, supernova ejections. Okay, so this is kind of one of the things which will happen. But basically what happens is that this can lead to material which is now enriched compared to what was the primordial original material, and this can go through this cycle. This is the cycle which can go inside a galaxy. Of course, galaxy is not an isolated system, it is interacting with the surrounding. So you can also think of mass loss due to large scale winds. That means not only you influence chemically the nearest neighbor to the stars, you will also influence the larger scale structures like IGM in this. So this is the basic picture. The problem is that, like what you know is you can model all of them analytically, because you know that if you don't know some number, it is 0.1. If the product has two numbers, 0.1 and 0.1, the product is 0.1. So this is what you will say that epsilon, eta, gamma, everything is unknown, but the product will be 0.1. So we have played this game some time back, but then I realized that it is not taking us anywhere. Okay, so that's why what we are going to do is that how to address this problem more realistically. Realistically means it's not going to be correct, but as realistic as we can try. So let me just start with this plot, because this is well-known plot for all of you. If you look at the luminosity function which has been discussed yesterday extensively, observed luminosity function, if you compare with the dark matter mass function, you assume that constant mass to light ratio is valid, then this is the well-known curve. It's in, say, nearly 20 years back, people have realized. So this curve and this curve are not different, are different. We have to make them same, so people just bend this way and this way. So bend it at different points. Other way of saying is that if constant mass to light ratio doesn't work, you say that mass to light ratio depends on mass. We don't know which mass, because that is going to change, baryonic or whatever mass, right? So this part, high end mass, we will say what is known as AGN feedback. Other way of saying is that we want to have a system which will heat up the gas in very heavy halos, and it will not allow gas to condense and form stars. So somehow you suppress this cooling and other things. So you need extra heating source, I will put it that way. But people call it as AGN, and I don't think anybody really understand what is AGN feedback. I also don't understand, so I am not going to contest very much here. This part, it is very interesting. You can do it in various ways. Again, you have to suppress the star formation in the low mass halos. So again, two ways of doing it. One is that you displace the gas from the high density region so that they don't satisfy Jeans condition and form stars, or you keep the gas there and keep them ionized so that their pressure is so much they cannot form stars. So there are two feedbacks people talk about. One is called supernova feedback. Second thing is what is known as photoionization feedback. So these are the picture there. You remember this, and I will come back to bending the thing at later stage, and we will use different physics to bend. So this is what I wanted to say. So coming back to JWST, this is well-known plot. Just imagine the redshift range of 7 to 13 or something. You are talking about time scales of 300 to 800 million years. But I was told that when we were doing this thing, there is a characteristic time scale in a galaxy called free fall time. It is of the order of 10 to the 8 years today. It may be 10 to the 7 years at that time. So it already puts the problem we are talking about tension. I never use tension because I don't work on cosmological parameters. We'll call it a physics problem here. The time scales are going to be problematic here. That's what you have to remember. Okay, having said this thing, let's go through some of the observational things, and I will highlight few issues we should be aware of in addition to luminosity function while modeling a galaxy. So these are the 4 highest redshift galaxies for which spectra are known, and we believe the redshifts are correct. So you can see that this is the spectrum, and we imagine that it should have gone like this because we believe in everything is a power law, right? Because another thing, if you don't know the functional form, it's a power law. Okay, of course linear, but second order is power law. So if you consider a power law, there is a break here, and people believe that this kind of break happens because you are at the rest frame wavelength of Lyman alpha transition, and these photons cannot come out of these galaxies to us because of whatever happens in the intergalactic medium surrounding these galaxies. So it's amazing. If we do it 10 years back, take one transition and say that I will measure the redshift, people will laugh, correct? But now we are saying that this is the correct redshift because this is what is being predicted in the standard framework of whatever we call cosmological, whatever, Big Bang cosmology, right? So we will go by that. So these are the farthest galaxies for which redshifts are measured. That means galaxies are there when the universe is about 300 to 400 million years old. So this we will say. The second thing is that we are detecting them because they are in a neutral universe. See, otherwise this thing will not be there, then you will not be detecting them because there are no other features which you can detect. By the way, I want to make a technical comment. JWST provides spectra, but they are at utterly low resolution. So detect lines and all are going to be extremely difficult. So we should keep this in mind. So it's also a technical issue. It's not only physics issue. However, JWST is very good if the redshift is around 8, okay, 8 or 9. You can clearly see nice, beautiful lines which you can use to characterize various quantities, like as I mentioned here, it provides optical to UV spectrum. That means you can characterize the amount of light which is present. You can characterize the amount of metals which are enriched because you are detecting oxygen, sulfur, nitrogen and all. You can also characterize the amount of radiation which is present because if you take resonance lines like magnesium 2 and all, the intensity is directly proportional to how much ions are present in the galaxy itself. It's like volume density of total mass of ions will be directly proportional to the recombination. So they will tell you about how much regions are ionized. That means what kind of stars you have which can keep them ionized. But you interestingly also detect forbidden lines and semi-forbidden lines. Forbidden lines and semi-forbidden lines are dominated by collisional excitations because standard excitations are not allowed. That means they probe what is the pressure in the medium. So it's very clear. If you are looking at spectra, you get much more information than looking at SEDs or doing luminosity function because you can now say what kind of stars are there, what kind of enrichment has gone through. See, I am saying 300 million here. If I am going to detect oxygen and nitrogen at a level of 1/10 of solar, it could have gone through at least 2 cycles of star formation. A typical cycle will last about 100 million years. So it's amazing for you to say. So these are the problem I want to highlight rather than saying that whether it is dark matter or not. You fix the dark matter, even then we have problem. That's the thing I wanted to go through. Of course, the way people measure redshift, I told you the same. Look at the spectrum here and the break here. You can now measure the redshift, and people are bold enough to measure stellar masses. They will tell you what is the mass. And people also know that if you measure stellar mass, you can tell what is the dark matter mass. I am very scared, but people are doing it. So this is what is leading you to the situation in crisis in cosmology. So we have to be aware of this. But I guess that you will hear more from on this photometry, what all can be done from Yogesh, I guess. Okay. So let me come to the luminosity function. It has been discussed yesterday. So I will focus on couple of these plots. One of the things which emerged from early observations of JWST is that we have large number of sources compared to what was predicted before. So what was the idea before is that up to redshift 6 you do all astrophysics. If you are actually measuring the evolution of number density of galaxies beyond redshift 6 up to 10, Hubble data suggested that you don't need anything else, you just look at the evolution of dark matter. It was absolutely, this number density evolution was just like number density evolution of dark matter. So people said that physics somehow freezes beyond this. So that has somehow it has to change. So I will just start like this. Luminosity functions beyond redshift 7. We have issues because this has been discussed, but I wanted to tell in recent observations or bringing the number density closer and closer towards what one thinks is the real life observations. So I will stick to a review kind of thing. So what do you think is the problem? Problem is that you measure photo Z. You don't know what fraction of these photo Z are correct. So that means like the number you are quoting is an upper limit in that sense. Second thing is that you do SCD fitting. SCD fitting has two issues. The break, if the break is occurring at low signal to noise region, you are not sure whether the break is a real break or some highly redundant objects which if you go towards blue end, no, signal to noise will be bad anyway. If you have ever used spectrum, you will know that if you go towards blue, any telescope, irrespective of, it is related to the instrument configuration. So the end where one is detecting edges, people don't probe them properly. Okay, so this is what we have to remember. Third thing is cosmic variance. The kind of volume people have probed is very small. So this is what is being told here. And look at this blue color plots and look at this. The difference between them is that one is about 4 pointings of JWST, another is 26 pointings of JWST. And there is a plot which shows that as you increase the number of pointings, that means you are increasing the volume probe, you find that the number densities are going down. So for some reason, people have picked. I think this is known to you, right? If you are, maybe some of the younger people don't know. When Hubble went, the same crisis happened at redshift of 5 or 6. Overshare published very massive galaxies from 10 to the 12, and there was crisis in cosmology to explain redshift 6 galaxies. There are several papers written, but slowly now they are all disappearing. They are all redshift 3 galaxies, wrongly identified when the spectrum were taken. So I will not jump into this conclusion and bandwagon. I think that is for people. Yeah. So that is the situation here. Then we need to worry about photometric calibration. It was also found out that the flux what you measure translate to luminosity. Since you are measuring at very large distances, even small error in flux will add to large error in luminosity because of DL square is very large. Okay. And I will just make a comment that don't trust any stellar mass estimation. They are wrong. Okay. It's clearly. So having said that, I will say one more thing which is interesting is that people are measuring sizes, and the size evolution is something like this. And typically 5 10 to the 10 stellar mass of galaxy has a size of less than kiloparsec. Again, if you do physics like me, because I can't think of higher end physics, you just to see that volume. If I take sphere, radius is 100 or 1/10. That means volume density is 1000 times more. Even if you say that I have the same scale height, this is 100 times more. And people know that it is very difficult to compress the disk gas to that, right? So because you are going to have the same Jeans criteria because mass is same. So it's very interesting for us to realize this. So if you want to do all these things, so last part, okay. Another one more complication I will do, and then probably the next one I wanted to concentrate on is related to these emission lines. These emission lines are now detected by stacking the galaxies. Suppose if you have 200 galaxies for which spectra are taken, you stack them in different regions, you detect them. What does one find? You can actually do one example I will show. You can actually do what happens to carbon to oxygen versus nitrogen to oxygen as a function of abundance here. So this is our local universe. Local universe, this trend is very much understood from the stellar evolution. So if you look at carbon to oxygen, it follows this trend which has been set by the local universe. Whereas if you look at the nitrogen to oxygen, this is the trend set in the local universe. I will explain why it is if somebody is interested. But we find that in the observation at high redshift, nitrogen is enhanced. This suggests that you have to go for a population which is slightly different. So, okay, I think I don't know. The last bit, one more, I have too many things to say. Maybe I'm worried that I have to go to what I wanted to do. The other thing which is complicated, maybe this is important for everybody to realize also. Other thing which is complicating is what is known as little red dots. Little red dots are the objects which are seen with red dots. If you go and look at the spectrum, they behave like a AGN, okay? But if you look at the blue part, you see they are like stars. The red part, they are like AGN. It is always ulta of what you see in nearby galaxies. Nearby galaxies, galaxies look red, quasar look blue, because it is the other way around. So if you look at the number density of these typical masses are of the order of 10 to the 7 solar mass. If you look at the number density per unit volume, it is 1/10 of what you see for galaxies, or 10 times more than what you see for population of AGNs. So if you trust that these are black holes, which is what people tend to believe, so you already have too many black holes to deal with at redshift of 7 or 8. So you will say we will deal with it, there is no problem. But the problem is that this population simply disappears at redshift 3. So it seems that there is a new set of population which we need to understand. So to understand all this, okay, we started, I think I have to say this, I will take a couple of minutes or 1 or 2 minutes just to say this. We started this, what is called the NICER IUCAA new simulation of JWST galaxies. We already hear about it, so I will not look into the details. This data will be available. The idea is that we can run this simulation in 10 days time up to Redshift 4. So if I have 100 days, I can do 10 at least parameter space variations. This is amazing to do, and just to apprise you of what kind of sizes we have, this is the thing you are aware of. This is TNG simulation, and you can see this is the kind of box sizes they use, and this is the kind of box sizes, this is the kind of number of particles. So our numbers are close to something like 2040 cube particles. This is what we are simulating, and the simulation boxes are 50, 100 and 250 megaparsec. Here we can actually do feedback variations, and so it's a standard picture to show we can do. This is for Yogesh, and he will name this galaxy at some stage. This is the Redshift, Redshift 6 spiral galaxy in our simulation. And this I will skip because these things you heard from, this is one thing I wanted to do. I'll just give you the power of such simulations. So this is the same galaxy in the dark matter. In one case, all feedback will go with some speed of wind. In another case, it will go with half the speed of wind. Other way of saying is that wind carries a momentum which is half that of momentum in the other simulation. This is what we can fix, right? We can fix that what kind of efficiency at which wind is propagated. And the same galaxy, it has 42,000 stars when the winds are slower. It has 26,000 stars when the wind goes faster. And you can see it is like a razor thin disk. If you see, is much more bulge. Actually, if you do calculations, you can see that the sizes of the galaxies are very much depending on the feedback we are putting. So I want to say that in analytical model, you can say that I will suppress this by doing this. If you do this, we run into difficulty of understanding the sizes of this thing. So, of course, these things were discussed. I will not go into these plots. The last plot I want to say is that this is the last plot. So we also are now able to do this calculation, which I skipped, and this is my last slide in that sense. So since this guy is sitting in the, each galaxy is sitting in the web of intergalactic medium, you can actually ray trace. You take each star and calculate what is the opacity it will face in the interstellar medium, intergalactic medium, before going to the intergalactic medium, circumgalactic medium and intergalactic medium. What we are finding is very interesting because maximum optical depth comes from the galaxy itself. Suppose you say that I remove the galaxy contribution by some physics, okay. You go up to some distance, then you look at the IGM. It is, what we are noticing is that it's very interesting. The second dominant factor is not the IGM, that's the clustered IGM. In the sense that there is an intermediate scale where is the enhancement of baryonic matter around this. At present, it is done in an ad hoc way. I would like to have a simulation done with a proper radiative transport, which is what we are hoping to do. So these are the, what more can be done. So these are the things we can do. Getting black hole number density correctly, we have some issue in getting the black hole number density. It depends on seeding and various things. We are, out of these 10 models, couple of models will explore how to get the correct black hole masses in little red dots and simultaneously explain quasar luminosity function at Redshift 6. This is our aim. We can produce millimeter, C2, C1. We heard in the first day all these lines which are seen from ALMA, it can be easily produced because we have all the tools, and this will not have alpha and beta. Okay, that's what. I don't know, people didn't get the joke. Reionization models, we have to do post-processing step. If we do it, we can also run the models with multiple radiation fields in this thing. That's what, patchy reionization. Dust on Lyman alpha radiative transport, I think this is going to be a very serious problem. People are talking about F escape. What F escape? F escape is 0 for continuum photon. You are talking about line photon. So I will be bit worried about Lyman alpha transport as well as Lyman limit transport. Radiative transport outside the galaxy is very interesting also. I think we want to look at metal lines. I think this is what Prakash is trying to do. Couple of simulations have come up to Redshift 0. And I will tell you that these simulations are far superior than some of the things you guys are using, like Sherwood or some bit of even Illustrious TNG. So these simulations can be available to people who want to work on it because it's going to be raw simulation. It's not going to be as good as Illustrious simulation in the product wise, but if somebody wants to work on it and get the products, we can study CGM, we can study cross correlation between Lyman alpha and galaxies and all. So I'll stop here.
Thank you. Time for questions. Okay. Let me start from here.
Yeah, I mean, these little red dots, if they are AGNs, they should show up in X-ray, right? But if I remember correct, that was one
No,
of
they
the
will not
issues.
show up because you see, they are red, right? They are red. So if the redness means there is dust and there is high column also. So X-ray will also be absorbed.
So then X-ray background will not be a problem, even if
Hard
you have-
X-ray will be a problem. Soft X-ray is not a problem.
So hard X-ray because they are escaping.
Yeah, yeah.
Okay,
Yeah.
okay.
So that we are not observing. That is the thing. That is one thing we calculated. That's what we are trying to calculate, hard X-ray and soft X-ray background. Other way you will say is that if it is isotropic dust or in one side, see that is other way of looking at. You put tilted red dots in all galaxies, then take 10%. That can be ruled out. So that we can rule out by saying that X-ray background will be there.
Yeah.
But if it is isotropic scatterer, then we cannot rule out.
And about these high redshift galaxies, I mean, what you are saying is even now when we call spectroscopic confirmation, that is also not very solid because the resolution.
Confirmation is solid. The individual galaxies are solid. Only thing I have is that, see, it is my ignorance. I am not blaming anybody. Is that I don't know how to calculate volume. See, converting one or two detection spectroscopic candidates based on color cut to convert to luminosity function, I have not understood. I will not say, so I cannot make a comment on that.
Hi, thanks for the nice talk. So I have two questions. Because you mentioned about ACD fitting problem, and you mentioned about high nitrogen in high redshift. How do you put this together? How much do you trust it?
See, high nitrogen is different ball game because I think don't mix to this thing. Nitrogen issue is I want to understand how to model N3 line. The N3 line, these guys are modeling through what is known as equilibrium ionization. But if I say the time scale is very small, why should I believe in equilibrium? I think that is what it is. It is not a nucleosynthesis problem. It is a non-equilibrium problem. So we will address it.
Chemical composition of galaxies.
We have to try here. I don't. I cannot say something which I have not done that. But I believe this is the reason.
So you were saying that we start to see emission lines by the redshift of 8 or something, and those two galaxies that are at the redshift of 14, they are identified with just breaks. But a new paper has come out like not too long ago by Naidu et al. And that galaxy is at around the redshift of 14.4 and it has multiple emission lines visible also. So
No, I think other multiple emission line visible is not a problem. Visibility of Lyman alpha emission is a problem. Because all other emission lines can be produced where they are proportional to what is the star formation. Because I mentioned that the density of gas is very high. When the density is very high, the recombination goes as n square. Okay. So if you simply scale ISM densities to that kind of density we are talking about, it's natural to get a lot of emission lines. I'm not worried. But what everybody is worried is that redshift 14, how come you are having Lyman alpha? Because Lyman alpha should not be seen. Because redshift 14 should be sitting in a very dense intergalactic medium. So that is the issue. See, 1 is never a problem. The error is 1 plus or minus 1, right? So we have no problem. If people find 10, we will worry about it. That will be my attitude because otherwise I will get BP tablets.
okay, one last question. Yeah.
So maybe I don't know this, but what is your concern about stellar masses from JWST? Is it that the SED fitting codes have not been independently calibrated by redshift?
No. ACD fitting code, see, stellar mass is not computed based on how many stars are there formed today. We need to know how stars are formed ever since the first stars are formed in the galaxy. This is known as star formation history. So people assume exponential increase, exponential decrease are constant or stochastic. So stellar mass, what you infer, in the late stage what happened is the late stage is dominated by, you are convolving with accretion which happened over a large time scale, there is no problem. When you are at very high redshift, you are still in this kind of fluctuating region where smooth curve I cannot fit through. If I want to say how star formation happened as a function of time, I have not yet reached a stage where I can follow a smooth curve. This is a simple way of explaining, because of which there is a huge degeneracy and people come up with whatever number you want. And there are nice papers recently, if you take them as stochastic process, the masses are dramatically reduced. Even for IMF I am saying, even if your IMF is correct, I am just saying that star formation history is much more crucial than this.
Okay. Maybe we can discuss more in lunchtime. So let's move on to the next speaker. Okay, and thanks to the speaker again. Yeah.